For years, humans have toyed with the idea of trying to harness the power of the sun. The idea of limitless energy has allured people throughout history, from the ancients to Hollywood. But what if we could recreate and contain this reaction on Earth? Well, countless companies in tens of countries are already clamoring for funding to achieve this, and whilst we've conquered nuclear fission and continue to do so with novel technologies, fusion always seems to be evading the clutches of our grasp. But why is this so? What are the key issues holding fusion power back, and will we ever achieve it in our lifetimes? In the 1920s, British astrophysicist Arthur Eddington suggested that stars produce their energy from the fusion of hydrogen atoms into helium, a highly exothermic reaction releasing vast amounts of energy. But it wasn't until the early 1930s when, at the University of Cambridge, scientists used a particle accelerator to fire heavier hydrogen isotopes at each other to react, and thus demonstrate the first ever human-made fission reaction. Like the nuclear arms and space race, this technology was quickly developed to try and use in a weapons capacity, but its potential applications beyond weapons in the energy space were far too promising. From the 1950s onwards, numerous teams around the world would try to replicate and contain these fusion reactions in the hope of harnessing the unlimited energy of the sun. From Soviet experiments at the Kurchatov Institute, the US-American Oak Ridge Laboratory, to modern-day investors like Jeff Bezos funding General Fusion, and Lockheed Martin who are testing their own fusion reactor projects, the race to harness fusion power continues. And whilst technology is being developed, engineers are running into the same fundamental problems that continue to impede fusion from ever working on a large enough scale. The sun's extreme conditions make it a natural habitat for fusion reactions to seamlessly occur. On Earth, however, things are much more challenging. To fuse two positively charged hydrogen atoms that really don't want to do so, you need extreme conditions, namely temperatures exceeding 100 million degrees Celsius and intense pressure. Yet, we haven't developed materials that are able to confine this reaction and let said reactions continue for long enough to actually create significant energy. Whilst modern experiments like those at the UK-based JET lab are getting there, having recently run a reactor to produce energy for 5 seconds, ensuring that these reactions can be sustained and controlled is the difficult part, as the physics of burning plasma, the state of matter needed for fusion, is still not fully understood. Power consumption remains another key challenge to these experiments, as the energy needed to start these reactions is currently far higher than the energy they produce. Harnessing and extracting energy from these reactions to provide an economic source of power remains a key engineering problem that is yet to be solved. But these challenges aren't stopping progress, with tens of individual or government-backed projects currently working on fusion reactors today. But progress doesn't come quick or cheap. The France-based ITER facility, the successor to the UK's JET project, will not see full-scale experiments until at least 2035, and is expected to cost over 20 billion euros. Whilst China's vision of building a commercially viable fusion energy project by 2050 is still just a vision. Whilst fusion always seems to be 20 years away, good progress is being made. But whether we will ever see cost-effective fusion-based power on a mass scale in our lifetimes is very much a question that can't be answered just yet.